if I'm going to produce my success in college and my success in my social life, how do I allocate my, my effort among those different outputs? Okay. Nonetheless, despite the fact that there are some uses that are more useful to think about things in terms of costs and some more useful in terms of production technology, there's a sense in which they're equivalent or dual to one another. And when economists talk about duality, what they're saying is that there's two different things which might be more convenient ways to look at things for some purposes than for others, but that are actually the same. And in fact, a lot of this course is about showing you the duality between a lot of verbal logic that you might use and mathematical logic that you use in other places. So I want you to understand those are actually the same as each other, even though one might be more useful for some purposes than for others. Okay. Now, this is particularly easy to see if we have only a single input. So imagine there's just one thing we can use to produce output, right? So our output is some function of our input, right? Maybe it's I to the gamma. Well, then the cost of producing output O is just the price of buying I multiplied by the inverse of this function, right? Because we can just directly get the output from the input. So we just invert it, and we get this, right? Now, when there's many inputs, there's actually two steps to this process. First, we have to figure out what are the set of inputs that achieve a given output in the cheapest way. So think about the problem, of going to college. When you say, well, it's this costly to me, you've sort of already implicitly in your mind said, well, it's this costly to me because the best way I can get that particular score is to do the following things. That was sort of your first step. And then from that, you derived what was the cost of achieving any given score, right? And then we call the cost of any given output that we have the cheapest way we can achieve that given output. Now, a natural place to start with this is with the extreme technologies above. So what is going to be the cost function associated with perfect complements? Marana's not here, right? No. Does anyone want to say what that might be? Again, remind me. Kevin. Good. Okay. Yeah.
Well, if they're perfect complements for each other,
yeah.
Then you need basically the same amount of code.
Yeah.
So you're going to want to set your two variables to be equal.
Exactly.
Otherwise, the extra is not going to make a difference.
Yeah.
So you want to be solving the equation that's the cost is equal to, or you're just trying to find a cost of the score of x plus x, so 2x. In other words, the same amount of both academics and
yeah, that's right. You just add together, the score is just the sum of the cost of the two things. Because you're always going to do them in constant proportions. And so you just add together the time that you spend on each to get the cost of achieving a given score, right? How about if they're independent of one another, Bob?
If they're independent of one another.
So if we have perfect substitutes, what is then going to be the cost?
So then the cost would just be, well, I'm assuming you're going to be picking one. If you only pick one.
So why would you only pick one?
Perfect. Oh, so wouldn't the cost just be, if the perfect substitute then is the one where it doesn't matter in between
Yeah.
Tx and Ta?
Yeah.
So basically, you can just want to just add how much you work on Ts times Tx, Sx times Tx plus Sa times Ta. Or if you do different times.
Does anyone want to expand on that? What's your name? Wesley, right? Right. Yeah. Go ahead, Wesley.
You're just going to choose whichever one's cheaper to you.
Yeah. You just choose whichever one's cheaper because they can be perfectly substituted for one another, right? And so you don't have any reason to favor one over the other. So you just choose whichever's cheaper. And so in this case, it's the minimum of the two. So you see how these things sort of reverse when you go from what's the cost and what's the production technology, right? And in fact, that's the same as in either or, right? Because in either or, you're also going to just choose one of the two. So as soon as you get to perfect substitutes or more substitutable than that, the cost function always looks the same, because you always choose whichever one is better. Yeah, go ahead.
I know that
Jacob.
one is always cheaper than the other. Couldn't one rise as you the cost?
Yeah, so we've
rises?
assumed linear
Okay.
costs of each of the things here. But if you had convex costs of each of the things, that wouldn't
You
necessarily be
use
the case.
whichever one's cheaper until
It becomes more
it's equal
expensive,
later.
and then,
Okay.
yes. You go along the path
Yeah.
where they have equal costs.
Okay.
And in the even more extreme substitutes case, you would, it's slightly more complicated than that, because you would actually like go even further along one until the like marginal product of the two is the same. Okay. Yeah, go ahead.
What about some costs?
Remind me, Matt, your math you as well?
Math Econ, yeah.
Yeah.
What about some costs in that though? Don't you want to say I've already put in 40 hours to athletics, so
Yeah.
I don't want to put in 1 hour to studying because it'll take me, another 40 hours of studying to get to the same place that I am now.
Yeah, so this is assuming that everything is flexible that you have. But if you have something sunk in, then yeah, you'd consider that. So if they were complementary, that would lead you to do more of the other thing. If they were substitutable, that would like lock you into a particular path. And if they were perfect substitutes, then it would have no effect on your future decision. Okay. Now, in the more general case, when we can't use these like sort of simple logics we were doing here, we have to mathematically solve to determine what the optimal mix of the things is and derive from that the production function. Okay, so in particular, we need to solve the following mathematical problem. We have to say what is the cost is going to be the cheapest way of achieving a given output. That is, we're going to ask what is the minimum cost, which is the time spent on x times x plus the time spent on a times a, subject to the constraint that we produce a particular score s. This is sort of the most classical constraint minimization problem. And I want to go through this, even though it's very mechanical, and you guys have probably seen something like this before, just to highlight to you what is the right economic way to interpret this problem. And it's relevant to your problem set. Okay. So the key thing is we think of there being an opportunity cost of failing to produce. You have to produce this much, right? So if you fail to produce it in one place, you're going to have to make up for that on the other. And so you think, what's the opportunity cost to me of not producing an additional unit, right? And then you minimize the total cost to you, including the opportunity cost. That's how we deal with any constraint like this, is we think of it as having an opportunity cost, and we minimize all the costs, including the opportunity costs, right? That's what we learned to do in the basic intuition of Econ 101. And the Lagrange multiplier, all that a Lagrange multiplier is a way of mathematically formalizing the idea that every constraint that we face has some opportunity cost associated with it. We usually call this a Lagrange multiplier, and you'll talk about the Lagrange multiplier in your problem, but I want you to understand that this is exactly the same as an opportunity cost. Nothing more, nothing less, nothing fancier. And so I'm really not going to talk much about Lagrange multipliers in this course, because we can almost always just think intuitively about what the opportunity cost of a resource is. And in fact, the Lagrangian equations can be just derived directly from that logic. The final thing we do is we solve out for what the opportunity cost is, and then we substitute that back in to determine what the actual levels of the different things are. Okay, so let me derive just from the logic of opportunity cost what the Lagrangian equations are, and I'm not going to write down any Lagrangian at all. I'm just going to talk through what the logic is, and from that we're going to get the equations that you would typically use to solve this. Okay, so let's call lambda the opportunity cost of failing to produce, right? And now what we want to do is minimize the total cost that we get from using each input including the opportunity cost. So what's the cost of using more x? Well, it's the time of producing more x. It's the time you spend on x, right? What's the marginal opportunity cost of failing to use x, right? Well, it's the Lagrange multiplier, our opportunity cost, multiplied by the marginal product of x, right? Because every time we decrease x, we are failing to produce quite as much, and we have to pay the opportunity cost of that. So we get that Tx is equal to lambda times the marginal product of x, which is k psi x to the psi minus 1 times a to the alpha. And what do we do for a? Well, we think the same logic. What's the cost of a, of doing more a? Well, it's the time we have to spend on it, right? But what's the opportunity cost of not doing a? Well, it's the opportunity cost times the marginal product of a. So again, that's alpha x to the psi, a to the alpha minus 1. Now, we know we need to produce a certain amount s, right? So how do we set the opportunity cost of things equal to each other here? Well, we know that lambda has to be the same in these two cases. So we can just divide through by this left-hand side, leaving alpha, and then equate the two sides. So we get Tx over k psi x to the alpha minus 1, a to the alpha is equal to Ta over k alpha x to the xi plus a to the alpha minus 1. We do the exact same sort of canceling we did before. And what do we get? That alpha x over psi a is equal to Ta over Tx. And that is a very nice little equation. So what that tells us is that if we have two different factors, the marginal rate of technical substitution between them is the ratio of their two prices, right? This is the marginal rate of technical substitution we had before. This says that if we can get more production, a little bit more production, by using one input, or the other input, we should use them in such a proportion that the additional cost of using one more input versus the other is the same. That is, that the ratio of the production that we get for the two of them is equal to the ratio of the price for the two of them, so that the use of $1 in any of the activities is the same. That's really just the intuitive idea of a Lagrange multiplier, right? Or of an opportunity cost. It's saying a dollar of time, a unit of time, gives me the same bang for my buck on the margin in any use of that, right? And also, that's exactly what the tangency conditions that you usually learn are. So if we have an isoquant like this, and we have a ratio of the two prices, which is given by some line, we're going to choose the point where these are just tangent to one another, because otherwise we would be able, if we chose a point, say, where it intersected,